Hi, hi everyone. This is Jem, and welcome to my presentation for the CGT 620 final project. My topic is cloth simulation, and for this final project, I implemented three checkpoints. The first checkpoint is the prototype of a cloth object. The second checkpoint is the collision between a cloth and object, and the third checkpoint is the self-collision detection of a cloth. So in order to implement the first checkpoint, I used the conventional mass spring model, which can be represented by the equation right here. So basically, this equation is computing the force for each particle. It is considering the gravity, the force of the wind, the force of the damping, and the force from the intrinsic property of the mass spring model. So this intrinsic property is basically generated from these three spring structure that is kind of holding the framework of the cloth. So the shear spring right here is basically prevent the cloth from immediately falls into a line, and the bending spring is something that is preventing the cloth from folding like a piece of paper. So so another thing we wanted to do right here is we wanted to use integrator to update the cloth system. So essentially the mass spring model is an ordinary differential equation that we wanted to solve. So if we naively use the forward Euler integrator to update the system, it's going to explode easily. So in order to avoid this, we simply limit the time step within a very small model, within a very small value. But we don't want that because if we're doing that, the clock is going to look like it's moving in a slow motion, and we don't want that. That's very unnatural. So that's why we wanted to use the RQ4 in Verlet. So basically, what this is doing right here is it's um, it's trying to approximate the root of the ordinary differential equation with relatively low deviation. So that is how we can update the system with relatively large time step, but remain everything stable. Um, but I don't know why my my archive for everything looks right, and for all the resources I can find online, I think my archive for is the method here is valid, but I don't know why. Maybe it's the problem of the parameter adjustment or something else. It's not working properly in my implementation, so I choose Verlet algorithm. The Verlet is using the position and the position from the previous frame and the acceleration and the time step and these four things to update. So so how did I implement the everything is so first I initialize the VBO. The VBO holds the information of all the particles, and then I pass the pointer of the VBO to the kernel. So basically the kernel right here is work very similar to the compute shaders in the OpenGL. It's computing using the mass spring model. It's computing everything, the force, the Verlet, the RK4, and it has everything, and it compute the position of the next frame and write it back to VBO, and then OpenGL take the VBO over and put it on screen. So another thing I wanted to talk about is the ping pong buffer because basically we are constantly worrying about the read-write collision, especially when we programming in multi-threading. So in order to solve this problem, we put barriers. We use atomic operations. We call a CUDA sync thread, something like that, between the read-write operation to avoid this problem. But these kind of operation could potentially hurt the frame rate, and I kind of don't like that. So I implement a ping pong buffer, which is it's a pretty nice trick. and very easy to implement. I just simply initialize two VBO pointer, and for each frame, I alternatively pass these two pointers to kernel function, and uh, and the kernel function is always read from the read buffer and write from the write to the write buffer. It doesn't know about the ping pong buffer. It's just blindly taking two pointers and just read and write to different ones. But by using this, we can avoid calling the barrier operations because the kernel function is always read and write from a different location. Right? And another good thing about this is so the write buffer actually contains the information from the previous frame. So that this is also how I used to use the Verlet algorithm, because you can see right here the Verlet is taking the position from the previous frame, and this is something I can get from the write buffer. So this is the output of my first checkpoint. So it can interact with the wind. I can change the draw call, the polygon with which I draw the cloth for debug purposes. So for my second checkpoint, all I need to there's only one question I need to answer, which is, can I detect a collision between a particle and a triangle? And the answer is yes. And because all we need to know is these conditions. Do we know the 3 points of a triangle? Of course, we need that. The normal of a triangle, yes, of course, we know that. The starting position of this particle and the predicted position of this particle. And we know all of them so that we can do this. And how we do this is, I'm not going to talk about this too much because it's going to take too long. So basically, the idea is whether on for each particle, I wanted to know which triangle is this particle passed through. So to know this, I just wanted to know whether or not the beginning position of this particle and the predicted position of this particle is on the different side of the triangle. If I know that, I know that there is a collision between this particle and the triangle. So basically, it just contains a couple of cross product and a dot product, and there we go. So if the collision finally returns yes, all I'm gonna do is I'm just gonna push this particle back to the surface, and this is the output of my second checkpoint. And for this one, I just did a little bit of optimization because I pre-compute the normal. I can compute the normal each frame real time, but I just think that's not worth it. So what I did is I pre-compute the normal and I store these normal into an array into a list in the global memory, and for each frame and for each particle, I'm going to access that when I'm computing the cloth object collision. But the frame rate you can see right here is kind of not low because the object is kind of it's just a cube, so there's not a lot of triangle involved. Also, you can see right here there's this clipping issue, so the cube is clipping through the cloth object. That is because the the resolution of the cloth is not very high. We can solve this by simply increase the resolution, but if we do that, I have to adjust the parameter to make the cloth look normal, like for a whole day. So that takes too long, but as long as we know the solution to this, I think we're fine. So for the third checkpoint is the self collision of the cloth is very tricky because so if we do in the triangle collision for each one of them, it's going to be really high. It's going to be really expensive. That's a nightmare. So I wanted to do something like this. I wanted to introduced a fast approach, but also the physical effect, the visual effect is not compromised too much. So then the idea is very easy. I simply treat each particle as a sphere virtually. So basically the cloth is going to look like this. So for each sphere, for each particle, I'm going to consider it as just as a sphere. So the cloth is going to be covered by a sphere, and the center of the sphere is this particle. So and still, if we traverse, so for each sphere, if I traverse, doing the collision by traversing all the other sphere is going to be very unwise because there's just too many particles, and I actually did that, and it hurt the frame rate so much. It immediately dropped the frame rate from 60 FPS to 20. So I introduced a little bit of optimization right there. So I what I did is I separate the space with cells. So for each particle, I am going to find in which cell is this particle locates. So then everything is easy, and uh, instead of traversing through all the other particles, all I need to do is I traverse through the neighbor cells which this particle is at. For example, like this S1. So we're in this sphere, we're currently controlling S1, and the S1 is at the number 17 cells. And we know that these cells from number 1, 2, 3, 4, 5, 8, 9, these cells are its neighbors. So we traverse through its neighbor cells to see if there's any particles right there. And that's it. So for the first one, if there's any triangles, no. Number 2, particles, no. Number 3, particles, no. Until number 22. Okay, there's a particle right there. And we check. Then we check these two um, then we check if there's a collision between these two spheres, and the collision between spheres is extremely easy and cheap. I'm not going to talk about this. So there's this is the checkpoint of my this the output of my checkpoint 3, and I changed the part with a kind of a cyan whenever there's a self collision detected. Yes. So basically, this is how it looks. But what I wanted to talk about is there's some very serious issues, which is when I push the cloth to a very complicated situation like this, you can see that the vertices are oscillating, and it kind of took me a while to figure it out, or what actually made this happening. So so the conclusion is what makes this happening is the second time collision. So what I implemented right here is so it works like this. So I am now controlling the S1 particle, right? So the S1 is going to be updated to S1 prime right here. And the S1 prime is colliding with S2. So there's a collision detected. And what I did is I pushed this S1 away from this S2 to S1 2 prime. But the problem is that the S1 2 prime is colliding with a third sphere, which is S3. And this is a situation that is out of the reach of my program. That is something I cannot detect. So in order to solve it, I wanted to introduce continuous collision detection. So to do this, so still the circumstance is the same. So this is the S1 is going to be updated to S1 prime, and there's a collision detected. But what I'm going to do, I am not going to push this S1 prime away. I wanted to find out the exact moment that this S1 is touching with this S2. So can we do that? Of course we can. So this is kind of a draft I did. So there's two spheres, and we know that these two spheres are colliding with each other in the next moment. So we know their position, we know their radii, we know their velocity, and we wanted to find out the delta time in which these spheres colliding with each other. So this is the condition. So I have S1 plus this and S2 plus this equals to the sum of their radii. And we wanted to, so if we solve this, we find the delta t, and I extended it, and finally we find out that it's actually a quadratic equation for the delta t, and we can put everything, or we can put this into code to solve this problem like this. So yes, so I wanted to talk about some future works of this project. I wanted to so the first of all, I wanted to improve is a higher cloth resolution, because with a higher cloth resolution, everything just look much better, right? It's just I have no time. I'm busy. I was busy with my proposal draft this week, so there's seriously no time for me to do this, because if I change the resolution of the cloth, I have to spend like a whole day to adjust the parameters to make the cloth look right. And another thing is the continuous collision detection. And for the cloth object collision, I'm thinking about to introduce the sign distance function. Sign distance field, because if we represent the object with which the cloth is going to collide with SDF, everything is going to be really fast. But the only issue is that the sign distance field is for some very primitive object like cubes, spheres, something that can be easily defined. If it's like for a rabbit, for a dragon, it's going to be really tricky, but we can do that. I'm not sure why I think this is it's kind of a very good issue to be solved, and that's all. Thank you.